Okay, let's do a problem. Find convolution of the following signals x1 of t convolution x2 of t. So I'm going to give you the waveform. So first one is x1 of t, so let me say it start from -1 to go to +1. This is t, and suppose its amplitude is 1. That is x1 of t, and x2 of t as a function of t, let's say it is 2 from 0 to 1. So these are the two functions, both are square pulse. We want to find out the convolution of these two signals. So the procedure is to evaluate the convolution integral. Okay, so x1 of t convolution x2 of t is basically equal to tau going from -infinity to +infinity x1 of tau. So that means you replace t with tau, that will give you x1 of tau, multiply it with x2 of t minus tau d tau. Now x2 of t minus tau, you need to basically plot it with respect to tau, okay, because the integration variable is with respect to tau. So you need to plot both x1 of tau and x2 of t minus tau as a function of tau. Okay, so let's do that. First one is very easy. We have this function, so with respect to t, I will now change it to tau, and I will write x1 of tau, and that function starts from -1, ends at +1, and its value is 1. Okay, so this is my x1 of tau. Now the other function, that is x2 of so how do we find the other function? So when you need to do a shifting operation and a flipping operation. Okay, so first thing, to get x2 of t minus tau, first of all, if you express x2 of minus tau, so if I suppose do the flipping operation first, if you do so, you have to be a little careful. x2 of minus tau, okay, so x2 of t is given, so whatever is on the right will go to the left, and whatever is on the left will go to the right. So from -1 to 0, this is going to be remaining at 2. So this is x2 of t minus tau, and now we can proceed to find out x2 of t minus tau. So how to go from x2 of minus tau to x2 of t minus tau? So we need to do a transformation. So x2 of t minus tau, you can write it as x2 of minus t minus t. T, if you replace it with the t minus t, so then that will be giving you t minus tau, right? I can rewrite this. So that means the transformation required is, so the required transformation is tau going to, in x2 of t x2 of minus tau, you put tau as tau minus t, or that is, you can say shift right by t units. That's what we need to do. Okay, so depending upon the value of t, So first of all, I'm going to divide it into various cases. Case 1, this thing, that is tau is negative, and negative, let's say that t is less than minus 1. So that means I have to shift x2 of minus tau by minus 1 or more than minus 1 to the left. Okay, so see, t is negative means I have to shift it to the left. T is positive means I am shifting it to the right. That's what this so here I can write if positive, then shift right, negative t means shift left. Okay, so here I have written shift right by t units, assuming that t is positive. Okay, if it is negative, you have to shift right. So I am taking a case where t is less than minus 1, that means more negative than minus 1. So I need to shift the second function beyond the minus 1 point. So right now it is from minus 1 to 0. If I shift it by more than minus 1, so that means shift left by 1 unit, more than 1 unit to the left, then what will happen is that there will be no overlap with x1 of t. So if I redraw this, the case 1, if I redraw this, so this is tau. Okay, here it is tau. I am shifting it beyond. So this is our minus 1. Earlier the function was like this. Okay, now I have shifted it more than 1 unit to the left. So it is somewhere like this. Okay, so this is 2, and so this is my t, and this is t minus 1. So t is a negative number, which is case 1. T is a negative number lesser than minus 1. Okay, so that is why I put t to the left of minus 1. So this edge was actually at 0. When you shift it, it will go to t, because you are shifting it by t, which is by a amount greater than minus 1 to the left. So now if you look at the overlapping region, when you multiply x1 of tau, so this is my x2 of t minus tau. Okay, if I multiply these two, what will it give? So the product x1 of tau, in this case multiplying s2 of t minus tau, is going to give you 0. Okay, so therefore you can say that even if you integrate your y of t for such case is equal to 0. So that is case 1. Now let's go to case 2. Okay, and case 2 is t is so case 2 case 2 is let's take t to be between 0 and minus 1. Okay, that is the next case. So I am taking t between 0 and minus 1. So in that case I will have to shift again to the left, but the resulting function will have some overlap with the x1 of tau. So this is my tau. Again I am drawing x2 of t minus tau, where tau is t is basically between minus 1 and 0. So here this is my minus 1. Earlier the function was like this. Okay, so now I am shifting it by t units to the left. So t is somewhere here. Okay, so this is t and this is t minus 1. The function value is 2. Now if you look at the overlapping area in this case with the first function starts from minus 1 to plus 1. Okay, so there is some overlapping area. and that overlapping area is given by this. This is the area that we need to integrate. So y of t is basically integral. So only place where you need to integrate is from -1 to t. Okay, -1 to t is the only area where it is integrating. The first function value in that case is 1. Okay, so this is 1. First function is 1 in that region, and therefore I will have to multiply 1, and the second function is 2, and that is into dt. So this is equal to 2 into integral dt is t, and -1 to t. Okay, so you can write it as 2t plus 1. Okay, when the shift amount is -1, this will become 0. There will be no overlap. Okay, so this is valid from less than or equal to -1, and it is valid. Okay, when I put t equal to 0, then I will get overlapping region as 2. Why? Because the entire region from -1 to 0, the entire region -1 to 0, you have 2 for x2 of t minus tau, and for x1 of tau it is 1. So 1 into 2, so it is 2, and width is 1, height is 2, so therefore the product, when you integrate, you will get 2. So this is valid even including 0. Okay, from -1 to 0, this expression is correct. Now case 3. So case 3 is we are shifting right, but not so much, but by an amplitude say less than 1. So let us shift it to the right. Case 3. Case 3, and I am saying that t is between 0 and 1. This is case 3. Okay, so in this case, if I draw x2 of t minus tau, so originally how it is starting from -1, and its amplitude is 2. This was originally the function, but now I am shifting it to the right by t unit. So whatever is at the 0 will go to t, because t is somewhere and 1 is somewhere here. Okay, so it doesn't go up to 1, it is somewhere between, and since it is shifted to the right, the new region is like this. Now in this region, if you look at the overlap with the first function, the first function is 1, from -1 to +1 it is 1. Okay, so when you shift it by an amount less than 1 to the right, the full part will overlap. The full part will overlap, because from -1 to +1 you have the first function, so the full part will overlap, and therefore in this case, when you evaluate the integral, okay, when you evaluate the integral, you need to integrate from, so if you look at here, this is from t minus 1, I'm integrating, so this is basically t minus 1, and then up to t I need to integrate, and the value that I need to integrate is the product. First function is 1, second function is 2, this is 2, so dt, so 2 is a constant, integral of dt is t, and you have to integrate from t minus 1 to t, so that is equal to 2 into t minus 1. Okay, t cancels, so as we expect, it should not depend upon t, the t will cancel, minus of -1 is +1, so this is equal to 2. So it is basically area under this, so the product will look like a square or a rectangle with width 1, height 2, so area under that will be 2. So this is case 3. Now we go to case 4. where we will shift it to the right, but t is greater than greater than 1, but let me write like this: t is greater than 1 but less than 2. So that is case 4. So in this case, if you draw this function, so what is this function? This function is basically x2 of t minus tau. So if I draw this function x2 of t minus tau for a shift to the right, so this is tau. So originally the function is like this. This is originally the function. Now we need to shift it by an amount more than 1 but less than 2. Okay, so let me denote this as +1 and this is +2. If I shift it beyond this point, so this is okay, so if I shift it like this, the new function will take appearance like this. So this is x2 of t minus tau, where t is between 1 and t. So where do you start? You end at t, and again this is basically t minus 1. So t is greater than 1. Okay. Now if I compare it with the first function, which starts at -1 to +1, the overlapping region is basically only this much. This is the overlapping region. So if I find the area under this, so that will give me y of t. So y of t is integral from t minus 1. Ideally the integration, convolution integral, is from -infinity to +infinity, but everywhere else this product is function is 0 except from t minus 1 to +1. Okay, so that is where it is equal to 2 dt. So 2 is constant, integral of dt is t, and t minus 1 to 1. Okay, t minus 1 to 1. So that is equal to 2 into 1 minus t minus 1. T into upper limit is 1, lower limit is t minus 1. So that is equal to t into 1 minus t plus 1. Okay, so this is equal to 2 into 1 plus 1 is 2, 2 minus t. Okay, so this is what we are going to get. So we can check what will happen if the shift is 2. So if the shift is 2, the overlap will become 0 because the left side of this x2 of t minus tau will come to 1, and there is nothing to overlap, and that you can see here. So this is also valid for this entire range. Now case 5 is the last case. We can see that if t is greater than or equal to 2, if you shift it beyond, then the overlapping region will be it will be 0. So if I draw x2 of t minus tau in that case, so this is -1 and this is +1. So originally the function started at -1. So if I it was like this, but if I shift it more than 2 units to the right, it will go somewhere here. Okay, so this is my t, and this is t plus so this is t and this is t minus 1, but there is nothing to overlap with the first function x1 of tau, and therefore we have y of t equal to 0. So we have found out y of t, the convolution result, in various cases. So combining all the cases, we can write down the expression for x1 of t convolution x2 of t, which is what I call as y of t. Okay, so y of t, case 1, that is t less than -1, it was 0, right? the first case, t less than minus 1, it was 0. Then from minus 1 to 0, it is 2 into t plus 1. So it is 2 into t plus 1 when t is between 0 and minus 1. And then the third case, that is what was the third case? The third case is 0 and 1, the result was 2. 0 and 1, the result was 2. So 0 and 1, the result was 2. And the fourth case, we had 2 into 2 minus t, that is when 1 to 2, t become 1 to 2. So t became from 1 to 2, okay. So there is less than or equal to also here, and 2 into 2 minus t. So 2 into 2 minus t. And the last case is 0 where t is greater than 2. So this is the different ranges, and it covers the entire time axis. Less than minus 1, then minus 1 to 0, 0 to 2, 1 to 2, and now we can plot this function very easily. So this plot is with respect to t, okay, and this is my y of t, which is equal to x1 of t convolution x2 of t. So less than minus 1, so let's denote, this is minus 1, this is 0, this is plus 1, and this is plus 2. So beyond plus 2 it is 0. Okay, so let me use a different color. So beyond plus 2 this is 0. Beyond minus 1 also it is 0. The function don't have any value. From 0 to 2, sorry, this is 0 to 1. This is 0 to 1. Okay, from 0 to 1 you have a constant value. So this is 0, this is 2. Sorry, 1 and 2. So from 0 to 1, okay, this range, we have the function remaining constant. Sorry. So this is the value of function. And then from minus 1 to 0, minus 1 to 0, it is 2 into t plus 1. So that is basically mx plus 2, 2t plus 2. So the slope is 2 and y-intercept is 2, that is this straight line. Okay, and then the second straight line is minus 2t, slope is minus 2, and then y-intercept is 4. So that is basically this straight line. Okay, so it is a, this is the shape of your convolution result. Now you can check the properties that we derived in the last class. The first thing that we said is that if the width of individual sequence is known, then we can find out the width of the convolution. So if you look at that, W1 was basically from minus 1 to plus 1, so that is equal to 2. Okay, how did I get 2? You subtract my 1 minus minus 1, so that is equal to 2. And W2 is from minus 1 to 0, so that is 0 minus minus 1. Sorry, let me see, it was from 0 to 1, so it is 1 minus 0, which is equal to 1. So W1 plus W2 is 2 plus 1, which is equal to 3, and you can see this here. If I take this as the width and measure this width, you will see that it is equal to 3, okay, which is basically W1 plus W2. So the width is satisfying the property that we derived. Okay, so that is one example. Any doubts in this case? If there is no doubt, we will proceed. So we are in the study of Lti system. We are looking at Lti system. Okay, and what we said so far is that about an LTI system, if you have an LTI system whose impulse response is known, okay, so this is an LTI system whose impulse response is given as the characteristics of that system. That means if you give delta of t, you will get h of t. That is what impulse response means. And if you give to an LTI system input x of t, a generic input x of t, then the output that you get for x of t as input is given by x of t convolution, x of t convolution h of t. So this is what we have said about LTI system. Now this is an integral, as I have shown you multiple times. It is from minus infinity to plus infinity, x of tau into h of t minus tau d tau. Now if on the top of an linear and time invariant system, if you have an additionally, if the system is causal, which it is because all practical systems are causal system. Okay, all practical systems are causal system. What does that mean? Therefore, h of t will be 0 for t less than 0. Okay, h of t is the impulse response. Impulse response will be 0 for t less than 0. Why? Because if you give an input delta of t, which happens only at t equal to 0, so the output cannot come before t equal to 0. It will start coming from t equal to 0. That is the property of a causal system. So all practical systems are causal systems. Therefore h of t, that is the impulse response, will be 0 for t less than 0. Okay, so h of t will have some shape. It will give some non-zero values only from t equal to 0. Okay, and secondly, so this is one thing, and secondly any input, any realistic input that we give to a system will start at some definite point of time. Okay, so suppose you are doing an experiment, so you will switch on your system at a particular time, and from then only the input is given to the system. Okay, if it is a circuit, you will give an input at some particular time when you start the experiment. Okay, so it will all start, all the all in practice, whenever we do an experiment, okay, whenever we give an input, we give non-zero value of input only from some point of time. Before that there was no input, or it is 0. Therefore we can say, therefore x of t, and that point of time we will call as the origin. Okay, that point of time we will call it as the origin, that is t equal to 0 point. So let me just specify that. So it will start at a definite point of time, let's say t equal to 0, and therefore for t less than 0, x of t is also 0. So h of t is 0 for t less than 0. Now we are saying x of t, the input that we give to the system, is going to be non-zero only from some point of time where we start the experiment, and therefore prior to the starting of experiment the input is 0. So using these two things, if you write therefore y of t integral tau going from minus infinity to plus infinity, this integral we have h of t minus tau d tau. If you incorporate the fact that h of t is 0 for t less than 0, and x of t is 0 for t less than 0. So if x of t is 0 for t less than 0, the lower limit of the integral is going to start from tau equal to 0, because x of t is 0 for t less than 0. Okay, and similarly, since h of t is 0 for t minus tau less than 0. Okay, so h of t minus tau, or what I said is that h of t is equal to 0 for t less than 0, and therefore h of t minus tau will be equal to 0 when t minus tau is less than 0. Okay, we can say this in another words. We can say this statement in other words: t less than, or let me say in terms of tau, tau is greater than t. Okay, so this same statement which I have written here, I can restate in this manner. I will take tau to the other side, so tau greater than t, h of t minus tau is 0. So here I have h of t minus tau. So this quantity is going to be 0 when my integration variable tau is greater than t. Okay, so I only need to integrate tau equal to 0 to tau equal to t, x of tau, h of t minus tau. Okay, so this integration limits are reduced. Instead of from minus infinity to plus infinity, if you consider it as a causal system, and if you consider it as a system whose input is 0 for t less than 0, then we get a more simplified expression where we need to integrate only up to from 0 to t. Okay, so that is an additional side note. Any questions? Okay, so if there is no questions, we will proceed. Now I am going to discuss another, so I am just going back to the signal part once again, and I am going to discuss another class of signals called exponential signals. Exponential signals. Now, earlier we have seen some class of signals: impulse signal and unit step function. Okay, and they had a relationship between one another. If you integrate the impulse signal, you get unit step. If you differentiate your unit step, you will get impulse signal. Okay, that was one class of signal. We could extend that class further also. Okay, so let me, before I go to exponential signal, let me extend that class of signal. So earlier, so that is a class of signal, class okay. So impulse, then unit step, so we will call it unit impulse, unit step, and next is unit ramp, then unit parabolic, etc. Okay, so this is a class of signal. They have a relationship with one another. So this is denoted as delta of t, and this is denoted as u of t. Okay, now this you can call it as u0 of t, and this is u1 of t, and this is called, okay, so let me, u of t you can call it as u1 of t, and then unit ramp is usually called as r of t. You can call it as u2 of t, and then parabolic you can call it as p of t, and then you can call it as u3 of t, and dot dot dot. Now the relationship is like this. Okay, so u of t, we know that it is basically integral of delta t dt from minus infinity to t, or you can also say this in a different way: delta of t is equal to d by dt of u of t. Okay, so now if I use the new notations which I have introduced here, impulse function is called u0, unit step is called u1, and then similarly u2, u3, etc. Okay, so similarly if I continue this to the next level, that is r of t is basically integral from minus infinity to t u of t dt. Or if I invert this, then I can say that u of t is basically equal to d by dt of r of t. Okay, so if I go one more step, so this is the relationship between unit step and unit ramp signal. Okay, now I can extend this relationship, same relationships. Okay, so p of t is basically integral from minus infinity to t r of t, and if I invert this, then I can write it as r of t is basically d by dt of my parabolic function. So since you have not seen this ramp function and parabolic function, let me just draw them. So first of all, let me draw the unit step function which you are familiar with. So this is u of t, and it is equal to 1 from 0, and all positive values it is 1. Now if I take this u of t and integrate it, what will happen? Integration is basically finding out the area from minus infinity to 0. The limit of integration r of t is basically integral from minus infinity to t u of t dt. That is what I wrote. So if I do this integration, whenever t is less than 0, you have integration 0. So there is nothing to integrate here. It is all 0. But from 0 onwards you have it 1. So if you integrate integration of 1, so we can say that for t less than 0, r of t is equal to 0. For t greater than or equal to 0, r of t can be written as from 0 to t, the value is 1 dt. Okay, so if I integrate 1, I will get t, and I put the limit 0 to t, so it's called t. So r of t, if I plot, it's equal to t. As t increases, the magnitude also increases. So this is t. Or in other words, you can say that r of t is equal to t u of t. This is an alternate way of writing, because for like negative values of time it is 0, positive values of time it is t into 1. So that is your ramp function. Okay, so that is how we plot the ramp function. Now what about the parabolic function? So let me say this as the ramp function. Now I am going to plot the parabolic function. Parabolic function. So what you do, you take your ramp function. Okay, so this is your r of t equal to t. So this is equal to t u of t for t positive, and before that it is 0. You take this function and integrate. So p of t is equal to integral from minus infinity to t r of t dt. Now r of t I can write it as it is 0 for t less than 0, so the integration variable, so let me say, so this is for t less than 0, this integration will give you no result, it will be 0, so p of t is equal to 0. If t is greater than or equal to 0, we are integrating from 0 to t. R of t is what? T u of t. T u of t is 1 in this case, so that is equal to this. So if I integrate it, we will get basically t square by 2 with limits 0 to t, which is basically t square by 2. So therefore p of t is equal to t square by 2 u of t. So we can write in this manner. So we can plot this function to see how the parabolic function look like. So the parabolic function, if I plot, so this is my t, and like this. Okay, so this is my parabola. Yeah, so this is my parabola. It goes like this. At 1 it should be 1. That is how you have to, sorry, at 1, t equal to 1, it should be half. Okay, so my earlier drawing was better. Alright, so this is say 1 and you have half. So this is my p of t, so unit parabolic function. Okay, so this is a class of signal, all this signal, so I can call this is ramp function. I will call it as u2 of t, this is u3 of t, and you can still continue, but we usually don't discuss anything beyond parabolic function. So all this function together we will call it as uk of t. This class of standard functions can be represented as uk of t, and they have this property, their relationship for different values of k, where k is from 0, 1, 2, 3, etc. So uk of t is basically integral of minus infinity to t uk minus 1 of t dt, or alternatively you can say uk minus 1 of t is the derivative of uk of t. So this is the first class of function. Okay, so they have this relationship. Okay, any doubts from this so far? Any doubts from what we saw till now? So let's take a break. We'll come back after 5 minutes from now, and we will continue with the other class of function. So this is a class which I have introduced earlier, but then I have generalized it into a class of function. Okay, only we have seen earlier impulse function and unit step function, but now I have generalized into a class of function which are related in this manner. Okay, so let's take a break.